Thank you very much for the invitation. Okay, so by an approximation to a blackboard talk. Okay, thank you once more for the invitation. It's a pleasure and an honor to speak at this seminar. I last spoke at the seminar in 2003, and I'm very happy to come back. My title today is Tate-Hochschild cohomology. The singularity category. And applications. Plan.
Все, это слышно.
I'd like to start with a reminder on cohomology. Then I will introduce Tate-Hochschild cohomology. And state the main field.
Yeah, I'm sorry to interrupt. People who are not speaking right now, can you please mute your microphone? Because otherwise there's so much noise. То есть, пожалуйста, не говорите, выключайте микрофоны, потому что иначе шума очень много. Спасибо. Там есть такая кнопка, там есть микрофон. Yeah. Sorry about that. This is the first meeting seminar in a Zoom format, and people aren't very used to it yet. Right. So.
Should I continue?
Yeah, I think it's fine. Yes, thank you.
А если мы захотим задать вопрос, то надо включить и выключить?
Да. Там есть кнопка специальная, если там, скажем, на таблете. Но просто когда у миллиона человек одновременно микрофоны включены, то вот идет такой шум.
Ну да. У меня его кто-то, что ли, выключил только что? Я его сейчас обратно включил.
Это может модератор тоже делать.
Ну, я прошелся, и тем, кто забыл, сейчас повыключал. Но его можно включать самому, конечно, лучше.
Хорошо, понятно. Я выключаю.
Ага, спасибо. Right, so let's continue.
Yes, and then in the third part, I would like to give applications. And these applications are two reconstruction theorems. For singularities, and this part is joint work with Zheng Hua from Hong Kong University. And let me show you a picture. So this is not yet. This is not Zheng Hua. Okay, here we have a picture. Okay.
The first one was not him, right?
No, the first one will appear later.
Okay.
Okay. So let's start with Hochschild cohomology. And in this presentation, I would like to follow the historical development of the subject. So if you like, it's Hochschild cohomology by its history. Okay. And for simplicity, I will work over a field. Okay. In the field, everything can be done over a commutative boundary. But for simplicity, let's stick with the case of the field. And then let's also fix a K algebra. And by this, I always mean an associative K algebra with a unit element. And but usually it will be non-commutative. And then Hochschild cohomology. Denoted by H upper star A. Was introduced, as the name suggests, by Tate-Hochschild in 1945. And in his article, he actually attributes it to Eilenberg-MacLane. So perhaps it should be called Eilenberg-MacLane cohomology, but it's probably too late to change that. And he defined it as the cohomology of the Hochschild cochain complex. So let me recall this complex. It has A in degree 0, K linear maps from A to A, A tensor A to A, sorry, from A to A in degree 1, and K linear maps from A tensor A to A in degree 2, and more generally, K linear maps from A tensor P to A in degree P. Okay, and the first two differentials, differential number 0 takes A to the commutator with A, differential number 1 takes a linear B with a map taking a tensor A tensor B, VA times B minus VB plus A times VB, and you can guess the higher differentials or look them up in any reference on the subject.
I'm sorry, is it really that old, 1945?
Yes, it's 1945, yes. And apparently Eilenberg-MacLane knew about it before. Yes.
Ah, okay.
It was a paper
in America, right? Somewhere.
Okay, so we immediately see, if we look at degree 0, we find that, of course, the kernel is formed by the elements which commute with all the other elements. So in degree 0, we get the center of A, Z of A, which is, of course, a commutative algebra in the actual way. And if we look at degree 1, what do we get? Well, as you can see, the co-cycles are precisely the derivations. The co-boundaries are precisely the inner derivations. So what we get is the Lie algebra of outer derivations of A. Lie algebra. Now, both of these structures extend to the whole of Hochschild cohomology. Let's first recall how this works for the commutative product. So for this, let's introduce the enveloping algebra, A tensor A opposite. Then, of course, modules over the enveloping algebra are nothing but bimodules over A. In particular, we have the diagonal bimodule or identity bimodule, which is that the algebra considered as a bimodule of itself. And then Cartan Eilenberg, in their book in 1956, reinterpreted Hochschild cohomology as the Yoneda algebra of the identity bimodule in the abelian category of bimodules. And then this is, of course, an algebra for the Yoneda product, which in this case is called the cup product. And the multiplication extends that on the center. The cup product multiplied by the cup. Now, surprisingly, it took 7 more years for people to realize that it's a graded commutative algebra. This was proved by Gerstenhaber in 1963. We showed two things. The first is that Hochschild cohomology as an algebra is graded commutative. Well, a modern argument for this would be, for example, to say that A is the unit in a triangulated monoidal category, namely the derived category of prime models with the derived tensor product, and then since A is the unit, it's graded, and the morphism algebra has to be graded commutative by the Ekman-Hilton argument. Now, this is not Gerstenhaber's argument. Gerstenhaber's argument was a direct computation at the level of code chains, and in particular, he examined the failure of this lift to code chains to be graded commutative, and in doing so, in examining this failure, he discovered a new operation on Hochschild cohomology, shifted by degree 1, namely, we discovered that it is a graded Lie algebra. And the bracket is nowadays called the Gerstenhaber bracket. Now, it's important to lift both the cup product and the Gerstenhaber bracket to the code chain level. And when you do this, you get part of a structure which was axiomatized by Getzler and Jones in 1994. Namely, they showed that if we take the Hochschild code chain complex with the lift to the code chain level of the cup product and the so-called brace operations, then what we get is what they called a B infinity algebra. Okay, why B infinity? You might think it's B infinity because it's after A infinity, but the reason is different. So the B stands for the name of the German topologist Hans-Joachim Bauers, who showed in 1981 that if we take the singular code chain complex of any topological space with coefficients in Z, then it carries a B infinity algebra structure, a canonical B infinity algebra structure. And notice that in both cases, the B infinity structure is related to a monoidal structure on the derived category of bimodals in the first case, monoidal structure on the derived category of sheaves with values in abelian groups in the second case. And okay, I should recall the brace operations. First considered by Kadeshvili, or first studied, let's say, by Kadeshvili in 1988. Okay, well, how does it work? Well, we take, say, a P code chain C, and we want to define its brace operations with a bunch of other code chains U up to W. What do? Well, we view C as an operation with P inputs and one output. Then we plug the other given code chains into some of these inputs. The W, we put identities in the other inputs. We add in suitable signs and we take the sum over all possibilities of doing this. Okay, so that's the base operation. And this B infinity structure contains all the information. In particular, we can recover the Gerstenhaber bracket. So for example, we recover the Gerstenhaber bracket of the code chain C or the code chain U just by taking C brace U minus or plus U brace C. And well, the second remark concerns generalizations. Well, these operations, in particular the Gerstenhaber bracket, are important in deformation theory, and we want to deform not just algebras, but more general structures, categories, and derived categories. So these instructions generalize from K algebras to K categories, which we should simply view as K algebras with several objects. Following Mitchell's famous paper from 1972, and they further generalize to differential graded or DG categories. Yes, and so the importance is that in deformation theory, in particular in the non-commutative setup, we want to deform not just algebras, but categories, categories of modules, categories of sheaves, and their derived categories. And we get a handle on derived categories thanks to differential graded categories. And so it's important to compute Hochschild's cohomology of categories, and here is one key result due to Bertrand Touraine, and I think independently to Wendy Logan and Michel van den Berg from 2005, namely the Hochschild cohomology of R algebra A identifies canonically via restriction with the Hochschild cohomology of the category of all A modules considered as an abelian category. So this is Hochschild cohomology as an abelian category, which by definition is, well, it's an abelian category with enough injectives, and by definition, its Hochschild cohomology is the Hochschild cohomology of the subcategory of injectives. And this further identifies with Hochschild cohomology of the derived category, more precisely the canonical DG enhancement of the derived category. So these a priori are isomorphisms of algebras, but they lift to the B infinity level.
Bernard, may I ask you one question?
Sure.
A question.
Yes, please.
This B infinity, is it kind of equivalent to E2 structure?
it's of course the key input when you want to construct E2 structures. I don't think it is strictly equivalent, but I have no reference for the fact that it is not strictly the same thing.
So
I mean,
do you mean that one implies the other?
Pardon? Whenever you
mean
have a
one?
B infinity structure, you also have an E2 structure. Yes, but the converse is less clear.
I see.
But it's not clear whether E2 is defined strictly. I mean, E2 depends on the choice of the model for the E2 operand in any case.
Yeah.
I think it only makes sense to speak about it up to homotopy, and then of course B infinity gives this. And the other way around is probably not true.
Yes. So maybe I mean, from a technical point of view, one disadvantage of the B infinity operand is that it is not a cofibrant operand, in contrast to the A infinity operand. So, yes.
I see. So does it mean that E2 operand is kind of imprecise thing? That's what Dima said?
Well, it is canonical up to homotopy equivalence in the homotopy category of operands. And I mean, B infinity, here B infinity is given very concretely. And then there's a morphism in the category of operands, let's see, from E infinity to B infinity, but I think it's not an isomorphism in even in the homotopy category.
Sorry, I thought that Hochschild cohomology is E2 operand, not E infinity.
Yeah, it's B infinity and E2. I hope I didn't say E infinity.
So if the infinity is a model for E2, yeah.
So whenever we have a B infinity structure, we have an E infinity structure, so which translates the existence of a morphism of operands from E infinity to B infinity.
Sorry, again, E2, not E infinity, right?
So, I'm sorry. E2. Yes, sorry. Thank you very much. Whenever we have...
I'm sorry, is it correct that B infinity has the same homology as E2? As far as I know, it's
not correct.
Brace operand, right? Brace is a part of, it's sub-operand of B infinity, right?
I think so, yes.
Yeah, so B infinity, it's not really the same thing, even homotopically, as at E2, right?
No, I don't think so. Unfortunately, I have no reference, but I don't think it's the same.
Boris, is it you?
Sorry?
Sorry. Who was it?
Шейст. И Рома Травкин.
Okay, so these isomorphisms look to the B infinity. Yes, the B infinity. Yes, by the result from 2003. Okay, and let me make the notation explicit. So mod A is the category of all right main numbers. And the full subcategory of injective main numbers. D will denote the unbounded derived category of mod A. And then this category has a canonical DG enhancement. And yes, so one remark, or two remarks. How should we view this isomorphism between Hochschild cohomology of the algebra A, the composed isomorphism between Hochschild cohomology of A and Hochschild cohomology of the derived category? Well, it's kind of a derived version of the, of course, very classical isomorphism between the center of an algebra and the center of its module category, the endomorphism algebra of the identity functor of the module category. But of course, we can also specialize to degree 0. So then we get the isomorphism an isomorphism between the center of A and the center of the derived category, which by definition is just HH0. And this is a desirable property, of course. And it's a property which does not hold if we do not use the DG structure. If we just look at the center of the derived category as a K-linear category, this is pathological. It's much too big, usually. For example, if one can compute the center of the derived category of dual numbers. Of course, one would like to find the dual numbers, but one finds a monster, an algebra of uncountable dimension. This is, the precise structure is this. It's the trivial extension of K by the vector space of uncountable dimension. This is a computation due to Henry Krause and here from proof.
Yes, it was modular epsilon squared, right?
Pardon? Epsilon squared, thank you. Yes. And to be completely honest with you, they compute the center of the bounded derived category, but that's already bad enough. And they have more examples in a similar vein. Okay, now let me come to Tate-Hochschild cohomology. Okay, for now here, let me suppose that A is an Noetherian algebra. Let's say right Noetherian. This isn't really necessary, but again, it makes the exposition simpler. Then we have the category of finitely generated modules, which becomes an abelian category. And inside we have the, first of all, we have its bounded derived category, dBn, the bounded derived category, dB of finitely generated models. And inside we have the perfect derived category. So the full subcategory of complexes which are quasi-isomorphic to bounded complexes with finitely generated projective modules. Okay, well, this is a thick subcategory. If the algebra is of finite global dimension, the two are equal, and then in general they are different, and it's natural to look at the quotient, the value quotient of these two categories. Well, this in the context of non-commutative algebras, especially Gorenstein algebras, this was first considered by Buchholz in an unpublished manuscript in '86. He called it the stable derived category, in analogy with the stable module category or stable category of Cohen-Macaulay modules. And in the geometric setting, this was introduced by Dmitry Orlov in 2003. Dmitry called it the triangulated category of singularities. Nowadays, it's usually called simply called the singularity category. And I will denote it by little sg of A. It's small sg because it's an essentially small category. And there's also a big one, big sg of A, which is, if you like, the derived incompletion of the small one. And you can recover the small one as the compact objects inside the big one. And because we have assumed that A is Noetherian, there's a very nice description of this category as the homotopy category of acyclic complexes of arbitrary injective A modules by a theorem of the main causa from 2005. So in particular, we see that we can compute morphisms in this category as homotopy classes of morphisms between acyclic complexes of injectives. An acyclic complex of injectives should be viewed as a two-sided resolution of its zero cycles. So we are just computing homotopy classes of morphisms between two-sided injective resolutions in the same way as one does in Tate cohomology, and that's where the name Tate-Hochschild cohomology comes from.
I'm sorry. In the last line, the isomorphism is for the category of compact objects or for the whole category?
I forgot the C here. Thank you. Yes, yes. Okay, more questions?
If instead of perfect, you consider, say, injective complexes and mod out them?
Well, in general, they will not be finitely generated, the injectives. But if you're over a finite dimensional algebra, over a finite dimensional algebra, you could do that, but by duality, it reduces to the same thing with projectives.
And over how was it, Noetherian? How you say it, Noetherian?
Gorenstein, or then the two coincide?
No, not Gorenstein.
In the Noetherian case, in the Noetherian case, usually the injectives are not finitely generated.
Right. So there is no reasonable category?
I think there's no reasonable category in general which you would get by quotienting this bounded derived category or something.
Okay, thank you.
Okay, now to introduce Tate-Hochschild cohomology, let's assume that the enveloping algebra is also Noetherian. Okay, and then this is, well, implicit in Buchholz Tate-Hochschild cohomology. Is defined, sometimes also called singular Hochschild cohomology, is defined as the linear algebra. In the singularity category of bimodules of the identity bimodule, in complete analogy with Barton Eilenberg's interpretation of Hochschild cohomology. Okay. And well, it's not hard to show directly that this is still a graded commutative algebra. Although the argument which I gave in the classical case does not apply, if you look at the singularity category of bimodules, SG of dA, SG of AE, singularity category of bimodules, this is not monoidal in any natural way. But, well, nevertheless, we can ask whether Tate-Hochschild cohomology has the same rich structure as classical Hochschild cohomology. Does it have a Gerstenhaber bracket? Does it come from a V infinity algebra?
I'm sorry to ask, yeah, I must have asked this before. Is it obvious why is it not monoidal? So
because the perfect complexes don't form a tensor ideal.
okay, unlike the, say, the representative
yes.
groups, where they do.
Okay. And yes, so does it have the same rich structure? And this was open for quite a few years. In particular, Buchholz and his students attacked this problem without success. And the solution was finally given by Zheng van Yuan in his thesis. And he first showed that there is a Gerstenhaber bracket. Singular Tate-Hochschild cohomology carries a canonical but very intricate Gerstenhaber bracket. This he showed in 2015. And then a bit later, we show that there is a V infinity algebra which computes it. The singular Hochschild cochain complex computing Tate-Hochschild cohomology with its Gerstenhaber bracket. So now I can use the other picture. And so this is a picture of Zheng van Yuan. And well, so we see that there's a complete structural analogy between classical Hochschild cohomology and Tate-Hochschild cohomology. And it's natural to ask whether Tate-Hochschild cohomology is not an instance of classical Hochschild cohomology. Can be interpreted as classical Hochschild cohomology of a more complicated object. And the main theorem is that this is the case. We have an isomorphism between Tate-Hochschild cohomology of A and ordinary Hochschild cohomology of the category, which is just the canonical DG enhancement of the singularity category. That's in analogy with the theorem of Tholen and Loven-Vandenberg, if you like. And this is an isomorphism of graded algebras. Okay, And now, well, now you see that we actually have two Gaussian-Haber brackets on one and the same gradient vector space. Yes, here we have the Gaussian-Haber bracket defined by Gaussian-Haber in 62. Here we have the Gaussian-Haber bracket defined by Zheng-Fan Wang in 2015. Of course, you would like to know that they correspond to each other through this isomorphism. And that seems to be a rather subtle problem. I don't know how to prove that. So let me state it as a conjecture. This isomorphism also lifts to the infinity level.
I'm sorry, Bernard, can I go slightly back? So
Yes.
if instead of all bimodules, you consider, say, right perfect ones, then this is also monoidal category, and it probably would give you the same HH, and then perfect complexes are monoidal ideal there, but it's only one-sided, right?
It's
only one-sided, and that's why the standard yoga doesn't.
I mean, the theorem shows a posteriori if you look just at the triangulated subcategory inside the singularity category generated by the identity module, then this triangulated subcategory is monoidal. So there is possibly a very small subcategory inside which is monoidal. A priori, it's not obvious.
Just saying both right and left perfect.
Yes.
Wouldn't that?
Yeah, I think it doesn't work. I have, yeah.
Okay. Okay. All right. Thank you.
Yes. Okay, so there is one positive result in this direction from last week due to Xiaowu Chen, Huan Li, and the same Zheng-Fan Wang. They show this they show that this is true for a very special class of algebras, namely the radical square zero algebras. So you take a finite quiver Q, you take the path algebra of this finite quiver, and you divide by the square of the ideal generated by all the arrows. So all the compositions of two arrows vanish in this algebra. And so here Q is a finite quiver. And for technical reasons, without sinks or sources. And in this case, this is, by the way, a causal algebra. So one has a nice description already of the derived model category. And then one also has a very nice description of the singularity category as the category of perfect objects over the leave-it path algebra associated with Q. And using this completely explicit description, one can compare the two sides. And it's a rather long paper, it's 70 pages, but in principle, so they do it by just comparing the two sides. And
is it related to the calculation of the Hochschild cohomology of the dual numbers?
I mean that, well, in the case of the dual numbers, I mean the dual numbers are a special case of this class. Yes, yes. If you take the quiver with just one vertex and one loop, then this algebra is going to be the algebra of dual numbers. Yes. So yeah, this is a very nice case because the algebra of dual numbers is actually Gorenstein, and then the singularity category is still going to be Hom finite. In general, for this class of quivers, the singularity category is Hom infinite. So, but still, yes.
Excuse me, did you say something about some Lie algebra or?
Leave-it path algebra. So you can describe.
What's that?
You can describe the singularity category of this radical square 0 algebra using the heaped path algebra. So more precisely, it is the perfect derived category of the heaped path algebra of E. So, well, you get the leave path algebra by, you take the curve Q, you give each arrow degree 1, and then you do a certain universal localization. Yes. So a localization process. Well, if you just take the curve with every arrow in degree 1, you get a description of the bounded derived category, and after this localization process, you get a description of the singularity category. So the arrow is graded. Path algebra. It's well, it's called path algebra, but it has relations, non-admissible relations, and it's well, it's a von Neumann regular algebra. So we are somehow not used to it, but the operator algebra is like it a lot.
Degree 1 means cohomological degree, right?
Cohomological, yes, yes.
Not homological, huh?
Yes, they correspond to x1, of course. Okay, then, well, to show you why this is probably, why the conjecture is probably not easy to prove, let me describe the isomorphism in the theorem. Okay, I need a bit of notation, so I write M for the DG version of the bounded category. Then I write S for the DG version of the singularity category. Then we have natural DG functors from A, one object DG category, the inclusion, the M, and the projection, the S, and of course the composition of the two is the zero functor automatically. And now, well, we want to compare morphisms computed in the singularity category of bimodals and the morphisms of the identity bimodal with morphisms computed in the derived category of bimodals over the singularity category. So here we have the corresponding identity bimodal, IS. Now this, by definition, is a localization of the bounded derived category of bimodals. And here we have the canonical projection functor. So we move this a little bit to the left. And this is a localization of the derived category of bimodals over the model category. The projection functor is given by the left adjoint of restriction along P tensor P. And between the two, there's a natural intermediate category, the derived category of A tensor M bimodals. Okay, here we can take the identity tensor I and left adjoint of the restriction. Now, if here we have I tensor 1, if we take again the left adjoint of the restriction, then this composition will vanish. So that's not what we want. So we cannot take left adjoint of the restriction, so we take right adjoint of the restriction. And then you show that this composition vanishes on perfect objects and so induces the functor between the localizations. And this functor does take the identity bimodel to be identity bimodel and induces an isomorphism in the algebras. Okay, and well, since this functor between the localized categories is induced by a composition of the left-derived functor with the right-derived functor, it is quite hard to make it explicit, and that's why it is probably hard to check that it preserves these subtle B infinity structures defined at the cochain level of apprelia. Okay, so now let me come to, are there questions so far? Okay, then let me come to the applications.
There is a very stupid question, but is it obvious that we could have started with not the A op side, but with the normal side, right?
Yes,
We could have...
it gives the same function. Yes.
Is it completely obvious? Or?
It's not completely obvious. No.
Okay, thank you.
Okay. So yeah, sorry, this is actually 3.
Sorry, who was A goes to where?
A goes to, well, maybe I should have written just S. So this is the identity bimodel.
Okay.
Yes. So yeah, it's just Hom viewed as a bimodel. Yes. So two reconstruction theorems for singularities. Okay, well, maybe I can move this to page. Okay, well, the first reconstruction theorem concerns isolated hypersurface singularities. So let's take S, the power series algebra of the complex numbers in n indeterminates. And we take R, quotient of S by some principal ideal, and we assume that this is an isolated singularity. And then the claim is that we can recover this isolated singularity from its singularity category if we know the dimension. So R is determined, of course, up to isomorphism by its dimension and the DG version of its singularity category. If we do need the dimension because of Knoerr periodicity. If we don't have the Knoerr periodicity, leaves the singularity category unchanged, but of course changes the algebra R up to isomorphism. So we do need the dimension, but once we have the dimension, it's enough to know the singularity category in order to know the singularity itself. So let me sketch the proof. Okay, well, we want to find some commutative algebra starting from a category. What can we do? Well, we look at the center. Okay, so by definition, this is the zeroth Hochschild cohomology of this singularity category. And by the main theorem, This is also Tate-Hochschild cohomology in degree 0 of the algebra R. Now, since we have a hypersurface, we can describe the DG singularity category using matrix vectorizations. Introduced by Heisenberg in 1980. And matrix vectorizations are two periodic, and therefore these Hochschild cohomology groups are two periodic. So this is also HH0 is also HH2R. Tate-Hochschild cohomology for all integers R, in particular for all big integers. So we're interested in the case where R is very big. And when R is very big, well, since the algebra is a Gorenstein algebra, it's a hypersurface, then this is isomorphic to classical Hochschild cohomology of R. This is one of the results of White's 86 paper. And so we reduced, sorry, in degree 2R, big degree 2R. And well, so we reduced to computing Hochschild cohomology of the hypersurface in high degree. And fortunately, this computation was carried out in arbitrary degree in the early 90s by the Buenos Aires cyclic homology group in 92. Villamagor, Andrea Solotar, and the brothers Cuccione. And what their computations give us is that we get the Turing algebra of the singularity. As you will recall, the Turing algebra is just the algebra S divided by the defining equation and all its partial derivatives. Okay. Okay, so we know the dimension and the Turing algebra, and now there is a classical theorem due to Mather and Yao, which tells us that from this information we can recover the singularity, the dimension of R and the Turing algebra. Determine the singularity by Mather-Yao's theorem, Steve Yao, of 1982. And well, they proved this in the analytic setting we need in the formal setting, and here it's contained in a paper by Royal and Fan from 2017. Okay, so this is the end of the proof. Now, if you're familiar with the literature, then you might be surprised by this computation and its result. Yes, in fact, the computation of the Hochschild cohomology of hypersurface singularity is already in the literature. Yes, it was computed by Dickerhoff. In 2011, he already computed this, and moreover, he found a different result. He found that the center of the, well, he looked at matrix vectorizations of this hypersurface singularity, and he found that this is not the Turing algebra, but the Milnor algebra, which is, by definition, the quotient of S by the partial derivatives, but not by F itself. So we get a different result. Why is this not a contradiction? Yes. Okay, well, does anybody have a guess why it is not a contradiction? Well, I can tell you. So Dickerhoff worked with matrix factorizations, and so this means that he considered this as a differential Z model 2 graded category. So everything, he worked in the Z model 2 graded category, whereas we consider this as a differential Z graded category. And this small difference in point of view gives us a completely different result. Of course, Dickerhoff's result is also very beautiful, but maybe not as useful because the Milnor algebra is not known to determine the singularity when we know the dimension. Okay, so now this was the first application. Now for the
Bernard, before we move on, can you please comment on this, maybe in some examples? Because to me, this looks very strange, the comparison between the two. Because the Turing algebra is just a quotient. I mean, if it were a cone, then
yes, yes. Okay. So there is a very simple example. Consider. So, consider. Consider just K, considered as a Z model 2 graded algebra. Yes, so it's K concentrated in degree 0, Z 2 graded. Now, if we consider the corresponding Z graded algebra, that's K u to the minus 1, where u is of degree 2. So in the Z model 2 graded world, it's just K. And if we look at the underlying Z-graded algebra, it's this algebra, K u minus 1, Laurent polynomial algebra. And so if you compute Hochschild cohomology in the Z model 2 graded world of K, of course you get just K. But if you compute Hochschild cohomology in the Z graded world of K u minus 1, you get something different. Yes. You apply Hochschild constant Rosenberg and you know what you get. So this is not K. Yes. So yes. So even So
but you see, what you get is something which is one-dimensional in each degree, if I
yes
correctly. So there are also odd degrees and even degrees. And in this
yes, there is a long exact sequence which links the two. Yes.
Okay, well, I probably should work it out for myself. Thank you.
Yes. Yes. So this is the. Yes. Okay. So the second application is to a slightly more complicated class of singularities. Let's take R a complete local isolated compound Duval singularity. So it is three-dimensional. It's normal and a generic section with a hyperplane passing through the origin is a Kleinian singularity. Okay, and then we assume that we have a smooth model, or more precisely a small frequent the solution. Isomorphism in codimension 1. Okay, so we have X and then stack R. And we have the exceptional fiber, which is a tree of rational curves. So F retracts a tree of rational curves, and associated with this situation, there is the so-called contraction algebra. Let's call it lambda. Introduced by Donovan and Wiens. In 2015. So this algebra is by definition the algebra which, it's a finite dimensional algebra, and it represents the non-commutative deformations of the exceptional fiber. Yes, so yes, since it's non-commutative deformation, it's in general a non-commutative algebra, and it determines many invariants of the singularity. This was work by Donovan Wiens, then work by Toda, then by Zhenghua and Toda. And this, the fact that it determines so many invariants led Donovan and Wiens to the conjecture that it should be itself a complete invariant. So it would be kind of an analog of the Turiner algebra. Here we don't need the dimension, the variety is of dimension 3 by definition, and this finite dimensional algebra should determine the singularity. Now with Zhenghua we have worked on this problem. We cannot quite prove this. We need a little bit of extra data in order to be able to recover the singularity from the contraction algebra, and we get it as follows. It turns out that this contraction algebra is a Jacobian algebra, the Jacobian algebra of a quiver with potential. With potential W. This was shown by Michel Vandenberg and one of his students, the Tannhofer de Bergsen. And Vandenberg in 2010. Okay, now the potential is an element of zeroth Hochschild homology of the path algebra, and the Jacobian algebra is a quotient of the path algebra. So we can look at the image of the potential in the zeroth Hochschild homology of the contraction algebra. In zeroth Hochschild homology of the contraction algebra lambda, and then what we can show is that if we take the pair consisting
homology or cohomology?
Homology. Yes, it's. I mean, it's a sum of cycles which are taken up to cyclic equivalence. So it's an element in homology. Okay, and this pair determines the singularity isomorphism, of course. And actually, we don't need the whole information on the pair. It's enough to know the derived equivalence class of the pair. Yes, I'm sorry. I made a mistake here. It's when the exceptional fiber is irreducible, they conjecture that the contraction algebra determines the singularity, and in general, they conjecture that the derived equivalence class of lambda determines the singularity. So we show this weakened version where we, as an additional datum, we need the potential. So well, it's some homological class which we need in addition. So it provides some evidence towards the conjecture. And
I'm sorry, this
yes.
Is this
What?
W or just W bar?
It's a W bar, thank you. Yes, that's what I mean. Yes, I mean it's natural to consider derived equivalence classes because, as shown by Donovan Wiens and Wiens, when you change the resolution, when you do a flop, then the contraction algebra changes by a derived equivalence. So that's why it's natural to consider derived equivalence classes. And well, one remark on the proof. So the proof is based on the first reconstruction theorem. And a non-commutative version of the Marvell theorem for quivers with potential. Which is due to Paul and Wilson Joe in 2018. And the second remark, well, as you perhaps know, I have been very interested in cluster algebras and their categorification using triangulated categories, and this is actually very much linked to this subject. Namely, it turns out that the singularity category of such a compound Duval singularity is a cluster category. It's the cluster category associated with the quiver with potential given by the theorem of the Vandenberg's theorem. So this is generalized cluster category as defined by Apreля in 2009. And so the categories which appear are very similar to the categories which appear in cluster theory. They are homofinite, two-color and admit cluster-tilting objects. There is one difference, which is the nature of the quivers involved. The quivers which appear in Donovan Wiens theory are quite different from those in cluster theory. Yes, so let's just look at two examples. So a typical quiver from Donovan Green's theory would look like this. Okay, so as you can see, it has lots of 2 cycles and it has loops, whereas the quivers in cluster theory are not allowed to have any 2 cycles or any loops. You do allow cycles of bigger length. So for example, you can take such a grid, let's say with k-1 rows and n - k-1 columns, and then you orient the edges so that all the squares become 4 cycles. Yes, this is a typical quiver of cluster theory. It's actually one of the motivating examples. This is the quiver which is associated with the cone over the Riemannian of k-subspaces in n space. And thanks to the fact that it does not have loops or 2 cycles, it's accessible to purely combinatorial methods, where so the potential, you can study it without really taking into account the potential, whereas in Donovan Lee's theory, the potential is really essential. Okay. So this is all.
So do you mean, excuse me, do you mean that Q and W is different in this second remark from Q and W before?
No, I mean, so the cluster category is well defined and is 2 Calabi-Yau and Hom finite whenever the Jacobian algebra is finite dimensional, and that's the case in both theories. In both theories, the algebras which appear are typically finite dimensional. But in cluster theory, they can also be infinite dimensional, but all the interesting examples, the main examples are finite dimensional.
But for Weems, it's 3-dimensional Calabi-Yau, is it not?
Well, the singularity,
I mean, I was thinking about like Ginsburg.
The singularity is 3-dimensional, but the singularity category is Calabi-Yau of dimension 2. Yes.
Ah, it's still 2. Because there is a theory of Calabi-Yau algebras, which was originally done by Ginsburg some time ago.
Absolutely, yes.
All dimension 3, right?
That was all in dimension 3. And I mean, Ginsburg introduced this famous Ginsburg algebra, gamma associated with the quiver with potential.
Yes.
And the generalized cluster category, by definition, is the quotient of the perfect derived category of the Ginsburg algebra by the finite dimensional derived category of the Ginsburg algebra. And this, so the Ginsburg algebra is, it is bimodule 3 Calabi-Yau. 3 Calabi-Yau as a bimodule. And this category is a 2 Calabi-Yau triangulated category.
Okay, so when you take the quotient, it drops from 3 to...
It changes, yes.
Okay, good. Thank you.
Yes, it's a well-known phenomenon, yes. When you pass to a stable category, the dimension changes. Yes. Okay. More questions or comments or remarks? Maybe I can stop sharing the screen and then we can see each other.
So this is kind of the end of the talk, right? Sort of.
This is the end of the talk, yes.
So let's thank the speaker. And
Thank you very much for your patience.
And if there are more questions, please feel free to ask them.
Yeah, sorry, I still didn't understand which quivers were different.
So the Donovan-Weems quivers have loops and 2 cycles, and the cluster quivers have neither loops nor 2 cycles. And well, and that's the difference. So yes, and that's the difference. But the categories which appear are very similar, because in both cases the Jacobian algebras are finite dimensional.
So it's basically the same theory, except the class of quivers are different. So you also have a potential, also cohomology.
Yes, it is. Yes, if you like, the cluster case is a it's kind of a more special class of quivers. On the I mean, you can classify all the quivers which appear in Donovan-Weems theory. Yes, they appear in families. It's a kind of ADE classification which you can give. I mean, it's more complicated than that, but in that spirit. So it's a finite class of quivers, but lots of different potentials, lots of possibilities for the potential. In cluster theory, you can take any quiver without loops and 2 cycles and some generic potential.
And it will be finite dimensional?
Pardon?
It will be, I mean, you said something's finite dimensional. So
no, in general, it is not going to be finite dimensional, but in the main examples it is, yes. So
there's some common context for the both theories?
For both, I mean, you mean for the finite dimensional and the infinite dimensional case?
No, for cluster and Weems Donovan.
I think the common context is that of the perfect derived category of the Ginsburg algebra.
But I mean, in the cluster story, there is actually much more going on, right? There is some relation to, I don't know, K theory even, or I mean, all sorts of geometry. But all that is probably specific to the cluster story, is it? So you don't expect it to.
Yes, I mean, there's an extremely rich and purely combinatorial theory in the cluster case, and because essentially things don't depend on the choice of the potential once it's generic. Whereas in the Donovan-Weems theory, the potential is very important. So yes. And usually you cannot just choose a generic potential to give you anything interesting.
Could there be some kind of characterization of cluster things by saying that they're kind of rigid with respect to change of potential in some sense? I mean, wild guess.
I think, well, they are just, I mean, the class which people consider is the class given by quivers without loops and 2 cycles and generic potentials.
Okay. And then this generality does not really, I mean, most of it does not really depend on the potential.
In this generality, most of it doesn't depend on the potential. Absolutely. Yes.
Okay.